sorry. So we now count over 700 members. Actually, we hit the bar of 777 members, and we keep growing. So here you can see my colleagues. So we're 16 people now, and we help the community to organize events, plan networking activities, find investment in the field of photonics, as well as we help with employment by managing the largest website for jobs in photonics. We also provide marking data and many more. Please don't hesitate to visit our website to find out about all the benefits of our EPIC members. And at this point, let me tell you a little bit about the sponsors of our event. We have 6 sponsors that represent the whole value chain of photonic integrated circuits. So number 1 is ficontec, which provides devices, microassembly, and the testing solutions for the photonics industry. These solutions are realized at the cutting edge and high precision production systems utilizing advanced automation approaches, regardless of the device material and target applications. Second sponsor is LioniX International that offers photonic integrated circuit modules based on silicon nitride waveguides. LioniX International supplies modules enabled by photonic integrated circuits based on its proprietary waveguide technology. They deliver a complete solution to our OEM customers, from initial design through volume manufacturing of products. Phix is a company that provides an assembly and packaging services for photonic integrated circuits. Phix supports cheap prototypes as well as high volume manufacturing, and our engineers help optimize the designs of the customers. Phix is a one-stop shop, fully tailored to your needs. OFC Specialty, material, fibers, and photonic experts, fully vertically integrated from glass performing design to complex photonic assembly. What can OFS do for you? Customized development and production of specialty fibers, cables, and assemblies. SUS MicroOptics manufactures high-quality refractive and diffractive microoptics in 200mm wafers for applications in automotive, photolithography, fiber optics, silicon photonics, and more. And finally, Nanoscribe is our sponsors. That is a world technology and market leader in 3D printing on the nano, micro, and mesoscale. Nanoscribe pushes the limits of 3D printing and challenges state-of-the-art in microfabrication. With that, I would like to tell you that we are talking about hybrid photonic integrated circuits, and you may be interested in the upcoming events of EPIC that include the event on LIDAR miniaturization in May and co-packaged optics for hyperspectral data centers, as well as VCSEL technology applications and the quantum communication and quantum key distribution event that takes place at the end of June. Besides, as the pandemic is almost over, we're now welcoming you to join us for offline EPIC events. The closest event is organized at the Laser World of Photonics show in Munich that happens the last week of April, and we'll hold several sessions, including a session on single photon sources and detectors, and a session on the new LIDAR technologies. So once again, we thank our sponsors of today's event, and I'm moderating this event together with my colleague Panagiotis Vergyris. And Panos, if you're here, could you tell us more of what will we see today?
Sure, Ivan. Thank you. Hello, everybody. Yeah, here you can see our agenda. So we're gonna have we have 8 speakers, and the time will be a little bit dense, but it's going to be very interesting. We're going to start with the JPICs, the pilot line for indium phosphide, the European pilot line, and we're going to continue with some foundries on indium phosphide and silicon nitride. We're going to speak also about how lasers, how hybrid photonics help new generation of lasers. And we are going to pass also to some speakers that comes from the packaging side. And then we're going to close with some hints from VPI photonics and design softwares for integrated photonics. And Ivan, we can pass to the supply chain, please. Thank you, Ivan. And here you can see all the people that there are today in our room that represent, of course, the full supply chain. We have some from the end user side, like Broadcom, from Microsoft or Alter Technology, and Huawei as well. We, of course, have all the people that are related to hybrid photonics and equipments, like testing instrumentation or lithography, surface treatment. We also have people from that are fabricating chips, like from different fields like quantum, optical communications, and programmable photonics as well. But it's not only what is important for hybrid photonics. We have also the system integrators. We have representatives from the materials. We have some people from the packaging and semiconductors, MicroOptics as well. And let's not go further on it because we have a very extended supply chain today. And Ivan, we can continue.
Sure, thank you, Panos. All right, so yeah, so this is the agenda for today, and I'm glad to invite our first speaker, Martijn from Eindhoven University of Technology, to give us an insight on the background of this topic, on how did we arrive here, and what are the joint European efforts in making photonic integrated circuits become true.
Okay, I hope you all hear me. Sound is maybe not optimum. I'm currently at Photonics Europe in Strasbourg at a hotel room, so I hope that works. Thanks for the invitation to actually give an overview of what we mean by hybrid integration and what is out there at the moment. And let me go to the next slide. What is our challenge here that we are looking at? In semiconductors, of which photonics is, of course, part, we face exponential growth. And this exponential growth eventually requires focus. So in semiconductors, of course, that's achieved by the well-known silicon semiconductors, the CMOS. So if you can do it on silicon, you want to do it on silicon. And the bottom line here is, of course, the more mature your technology, the more complex your technology, the lower the diversity in technology platforms that can actually sustain this exponential growth. Now, in photonics, of course, we see a similar trend. In photonics, currently, there seems to be sort of a focus on three major platforms. You might even argue two, silicon nitride and silicon photonics, both fabricated on a silicon substrate wafer. So actually nowadays both called flavors of silicon photonics. And of course there's indium phosphide-based photonics, 3,5-based photonics. So there are still, let's say, 2 or 3 major platforms. But why is that? Well, of course I put it in this well-known table, but I'll just go to the next slide to highlight a few of the main differences here. These platforms are complementary. There's no platform that can actually serve all needs. And some of the most well-known, let's say, holes in all of these platforms are, there's no laser in silicon photonics. Even in a wider context, silicon nitride, there are no actives at all in silicon nitride, natively to the technology. Indium phosphide, of course, has relatively high loss. There's no ultra low loss performance there, both for the components and the waveguide loss. And of course, indium phosphide, as we know it, does not really allow for the very large scale integration. So all of these things mean that there are various technologies out there and they are complementary. And eventually we need to combine in various ways. And actually the next slide gives an overview of a lot of the technologies or the techniques out there, how to combine. Well, if you think about silicon photonics, traditionally, there's a micro package containing a laser added. That typically gives you a laser, but it doesn't give you a lot of scalability because adding more lasers, it scales, let's say, linearly, not exponentially. There's, of course, hybrid integration. Instead of combining a silicon or silicon nitride wafer with a laser, you can actually combine it with a whole photonic integrated circuit in 3.5, an array of lasers, or an array or a laser plus a modulator, etc. I will highlight a little bit also later why this is relevant for the YAPIX pilot line. A sort of new kid on the block, but which might actually see quite some exposure in the coming future, is transfer printing. I'll park that. I go to the next slide and discuss that a little bit better, because I don't want to leave out two other ways of integration: heterogeneous integration, die bonding, wafer bonding of 3.5 material on top of silicon. Of course, that is becoming very mature. Intel is bringing that to the market. Juniper through Tower is bringing that to the market. It is, of course, a very specific process. So yes, it scales well, but it's an additional kind of process that has to be built from the ground up. And the final one, but that is still very academic, is heteroepitaxy. So basically the monolithic integration of 3.5 on silicon. Sort of a holy grail. We are not there yet. So let me give a little bit of attention to a European project that we run on transfer printing. Transfer printing is basically fabricating devices, coupons, active devices on wafer scale, transferring these through a stamp with a relatively large volume, so multiple units, and then aligning and bonding these to a carrier wafer that contains passive circuitry like silicon and silicon nitride. So there's a far more scalable way than micro-package kind of approaches. Challenges are, of course, the alignment that is required here. And this technique has been, among others, pioneered by IMEC, but in this Inspire project here, we're really trying to get this to the higher maturity level so that it can actually become available to the industry. And this project is called the Inspire project. So I just wanted to have one slide to highlight that before I go to a final slide. So I only have 6 minutes, so I very quickly jump to a conclusion. We need a combination of technologies. There's no platform that can do everything. Eventually, the target application will be a driver on how to do it. But the manufacturing and cost requirements will eventually determine what kind of integration technique is to be used. And in the context of hybrid integration, the topic of this meeting, I want to stress here, and I think in the next talk, Nazanin might go in more detail, but I want to stress the advantage of having a pilot line on indium phosphide 3.5 integration, because this not only allows us to actually have lasers connected to your silicon and silicon nitride, but also at a relatively mature stage, relatively, let's say, off-the-shelf technology, not only have lasers, but lasers with modulators, maybe lasers, pulse lasers, for example, arrays, well, you name it. There's far more flexibility in that. And I think that is key to hybrid integration as I have now defined it here. That already brings an end to my very short talk. So I would like to thank you for that.
Thank you very much, Martijn. And thanks a lot for setting the ground for today's discussion. Actually, I'm very curious about the YAPIX European pilot line. Could you expand a little bit more on that? What can it give to our members, and what could members of EPIC could bring to this pilot line?
Yeah, I think what it gives that in my last few phrases I explained that it's a next level of hybrid integration where instead of just adding a laser, the pilot line makes use of active-passive integration. So it does not only offer the passives, but also not only offer the lasers, but also all kind of modulators, photodetectors, etc. So far more functionality that can immediately, as a chip, be coupled to, for example, a silicon wafer. For example, I think we even have some packaging partners here. Well, one of your sponsors, I think, phix, is, for example, specializing in such kind of packaging. So what the pilot line can offer to the JPICs partners is about that. I think what the pilot line is for mostly looking for are also credible business cases. What are the real business cases that can benefit from this? So who are the first ones who want to scale beyond that single laser that is connected to silicon, or maybe 2 lasers? Who really needs this additional functionality? Those kind of, upcoming future customers, that is really what the pilot line is looking for.
Okay, that's very clear. Thank you. I'll let you actually answer this question in the chat, because people are questioning how is JPICs then different from a large company as TowerJazz Semiconductors, for example?
That's a good question. I think to a large, first of all, TowerJazz at this moment is working on silicon, and there will be, as far as I know, there's some heterogeneous integration approach. So the scaling here is far larger. Sounds very attractive. I think the harsh reality is that at this moment, we do not have that level of, we don't need that level of scaling yet. Also, I'm not sure how far these components are actually dialed in. The pilot line for JPICs is not a hybrid integration line. It's a monolithic indium phosphide integration, photonic integration pilot line. So it actually serves also customers that just want indium phosphide substrate. But we are highlighting here in this particular meeting the additional benefits also for hybrid integration.
All right. Thank you very much. Just to remind you, if anyone has a question, you can just use a raise hand button, or at this point you can just kick in and ask your question. If not,
I have a question. So I asked. So this is Wilfried from Swiss MicroOptics. I mean, JPICs is a great idea, obviously, for small scale or for starting things, keep things going. But both Juniper and Intel said now that their heterogeneous process is now basically like an open source process. It's not fully approved yet. It's still under approval. That's what we learned at OFC. But at the same time, they want to make a PDK. So it is a heterogeneous process with indium phosphide on silicon. And so the question is, I mean, how are you going to work with them, or are you going to be in parallel, or that was more my question. So can you learn from each other?
Yeah, I think learning is of course hard, and of course I think a lot of these questions you should also ask in the next talk, because Nazanin is actually representing a foundry. Of course, I'm let's say just an academic. I'm not making the stuff here. I think I come back to my previous point. It can be accessible, but I will bet you that at certain moments you should be able to pay for it, right? The process development, the development into the circuits that you need, the trajectory that is required to actually get to a product that will require a few iterations. I'm willing to bet, but again, I'm just a professor, right, an academic. I'm willing to bet that a JPICs pilot line is probably an order of magnitude cheaper.
I see. Yeah, definitely. Okay, thank you, Martijn.
All right. Alchemy from Antwerp Space, do you have a question?
Yes. Hi, Martijn, and thanks for the nice presentation. One question for me here. What is the TRL level for this transfer printing method? And is this integration method optimized for a specific application? Can you also elaborate a bit on the Inspire project, what you're going to achieve there?
Okay, I'll try to keep it a little bit short. Quite some questions. TRLs that we would be aiming for here are to make it, to transfer it to more mature partners like Smart Photonics and get it away from the purely academic. we will not, within the Inspire project, which will end in 2 years or something, we will not bring it to, let's say, TRL 7 pilot line level. We should be ready to actually start such an effort. So we are looking for the methods now to make it mature, if you understand what I mean. So that's about the maturity of this transfer printing. The specific applications are the ones that require very low loss, for example, and actives. And you can think about applications that require very low noise lasers, for example, for fiber sensing. You can think about, of course, the whole field of microwave photonics. There it's absolutely essential. But you can also think about applications in optical switches for data centers, where at a certain moment you have to cascade so many components, and you need those actives in there, that you really need to start thinking about integration density, component loss, etc. And then the low loss part and the integratability of silicon and silicon nitride come into play with the active functionality of 3.5. So those are 3 specific applications that we are currently optimizing it for.
Okay, thanks. That's very clear.
Yeah, thank you. Dieter from TU Berlin, just briefly, if you could. And you need to unmute yourself.
Presently, we're producing billions of surface emitting lasers per year for optical interconnects. Can you comment about the integration of such lasers with drivers?
I can't specifically. I can imagine that all the methods that I've just been discussing, a lot of them would also apply for surface emitting lasers. Actually, that has already been shown, at least in literature. You would have a little bit of different kind of coupling, of course, from layer to layer, but for a lot of application, that is obviously a very valid approach. Probably, though, you mostly would use the passives then, the silicon or the silicon nitride, as sort of interposers, because there's a different quality level, of course, involved with surface emitting lasers and planar lasers. So you would use them for slightly different use cases.
Yeah, it's easy actually for using pick and place. And of course, what is most important is the energy efficiency of the connection. Presently, the modules are controlled by the energy consumption of the driver and not of the laser.
Yeah, no, but that's exactly the case. So if it's a very short distance and very energy efficient, then of course that's a very valid approach.
Yeah, very short means up to 2 kilometers single mode.
Oh. Sorry, I have a lot of devices here.
Okay, thank you. That's fine. I'm done.
Okay, thank you for your question, Dieter, and thank you, Martijn, for setting the ground for this discussion. So you've mentioned the 3 major platforms for photonic integration. That's indium phosphide, silicon nitride, and silicon, of course. So I think we should continue with the talks from the representatives of foundries for those materials. And with that, I'll pass the word to Nazanin from Smart Photonics. Nazanin, could you start sharing your slides?
Yes.
Thank you.
You see the correct screen?
Yes, just make it full screen. Thank you. Go ahead.
Very good. Okay. Well, thank you for the introduction and invitation. I typically don't sound like this. So if there is anything that I'm not able to well communicate over the next 5-6 minutes or in the QA section of the meeting, please reach out to me after the fact and I'll be happy to answer you. Okay, so I'll start with a quick introduction of our company, Smart Photonics. We are an independent pure play foundry. As a pure play foundry, we're 100% focused on manufacturing for our customers. So that's one distinction, and I think I'd like to make, because customers are sometimes not aware that there are the two different types of foundries, the vertically integrated and the pure play. So we are pure play, so we don't have our products on the side that we are manufacturing. So it's 100% focused on service and chip manufacturing for the customers. And we're also focusing on indium phosphide manufacturing. So in that sense, we're in a very unique position in the industry, because we're the only pure play foundry of indium phosphide chips in the world. We are pretty well supported by the Dutch and by EU public funding by more than 200 million euros so far. And we've got a pretty long history in photonics. We come from Technical University of Eindhoven and Philips, and we have been growing since we established. We've been growing our team, our tool base, our foundry, and this is to support customers on multiple fronts. On the R&D stage, on the prototyping, to make sure customers have something to present to their stakeholders, a functional sample. The next stage, so that they have, they're able to test the market traction, and we're also able to take our customers all the way up at the scale of production, so high volume chip manufacturing. Now, typically you see challenge is what drives change. So right now we have a lot of challenges. We've got the challenge in digitization of the society, global communication, Internet of Things, Industry 4.0, mobility, and last but not least, the energy crunch and the climate change. All these challenges they're looking for is an integrated circuit, a photonic integrated circuit, what we call PICs. Why? Because it comes with a lot of advantages over discrete photonics or the electronic ICs. Namely, it's able to transfer more data at a higher speed. It's able to do it more reliably using less power and lower cost. And it's also able to do it with much smaller form factors. Now, I'd like to take a quick step back and stress that integration aspect. Because when you think about the electronics, it wasn't the electronic components themselves, per se, that enabled, it revolutionized technology in the world we live in. It really was the integration of electronics on a single chip that changed the world. So I'd like you to appreciate that while so much can be done with photonic components, it's really the integration of the photonic components on that single chip that allows you that efficiency, and you're able to do it on indium phosphide monolithically on one single chip. And again, we see that being able to enable the next period of technological revolution. So Martijn commented on this in his presentation. There are multiple platforms. We see the main two platforms being the indium phosphide and the silicon photonics platform. Now, the drivers of indium phosphide adoption are two main things. One is complexity. If you're looking to have chips where you require higher chip complexity, so that means if you're looking for integrating a lot more actives, lasers, modulators, amplifiers, that's one reason to choose an indium phosphide platform. And the second one is if you're looking for higher performance. So if you're looking for higher speed modulators, if you're looking to have lower loss connections to actives, again, that's the reason to be going towards indium phosphide. Of course, there are other reasons you may want to use different platforms. So if you've got, for instance, a really dense, but all passive components that you'd like to integrate with very few active components, absolutely silicon photonics would be the more preferred option. But if on the flip side, you're looking, for instance, to manufacture a coherent transceiver, you're again looking for more complex circuits where you've got a lot more actives, then definitely indium phosphide would be the preferred option. So we see photonics right now being very complementary to electronics in enabling new technologies. And this integration is quite intimate. So what you're looking at is you're looking at a lot of these technologies, these stacks of technologies that are enabling the next generation of devices and products, essentially. Very similar to chiplets, the system in package in electronics. where in these stacks, one will be the indium phosphide photonic wafer or chip. Now, the main drivers to go towards hybrid integration is to be able to take advantage of multiple technologies, obviously, to have reduced costs and be able to take advantage of the functionalities of indium phosphide on a die-to-die level. Next level from using a discrete component of indium phosphide on a silicon photonics platform, for instance, would be what Martijn referred to, where you're looking at coupons, where you're really looking to incorporate dense arrays of complicated combinations of very closely placed amplifiers or modulators, where you're really, again, making use of monolithic integration, but then able to print it on a different platform, where you're able to reduce the poor interface with absorption, reflection, scattering between your silicon guides and the functional devices that you've transferred. Again, another layer would be looking at self-aligning microstructures. In this case, you're looking at placement of waveguides, for instance, with less than 5 micrometer accuracy, I believe, where they're able to self-align and lock into place with less than 50 nanometers. So you're able to take advantage of passive alignment and have, for instance, an optical power variation of less than 1 dB, which is quite impressive. But really what you're looking at, and we see the trend to be, is this wafer-to-wafer assembly, where you've got this intimate integration of photonic and electronics together to be able to further improve the bandwidth, speed, energy efficiency for the next generation of devices. Really, what I'm trying to focus on is just the direction of this technology. Its hybrid integration is going away from this chip or die level integration, where you're looking at, for instance, a discrete indium phosphide laser on a silicon photonics wafer. We're moving away from this towards a wafer level integration. So we're looking at indium phosphide photonics wafer being integrated with silicon electronics wafer. Now, Martijn referred to this, and it would definitely be a remiss if I didn't talk about this. Now, with JetX, it isn't a pilot line that's focusing on manufacturing of indium phosphide chips. It's very much focused on technology readiness levels 5 to 7. And really, I think the main goal of JetX is to transform the PIC industry, to take it away from a vertically integrated model where you've got all the skills in-house within a very few businesses, to turn it into an open access where you've got a horizontal model. You've got a lot more service providers that are able to provide a service. And this is for 4 main reasons. One, to be able to accelerate the uptake of the PIC technology, to do it much faster with fewer design cycles from design all the way to packaging, to also have a sustainable production line in Europe, but the service is obviously available globally. And lastly, the more important thing is to be able to have this as a by sharing process optimization across products. Now, obviously, at the heart of the JetX pilot line are the foundries where we're doing the chip manufacturing, but we're very much intimate with other design softwares, multiple design softwares. You see a few here with design houses. We work very intimately with testing companies, industries, or consortiums. And lastly, with other packaging companies and also packaging pilot lines. So again, this is just to make sure we're supporting our customers across the value chain, and again, collaborating very closely with one another. And lastly, in terms of what we can offer you, I think talked about it in depth. What we're looking for is we're looking for companies that want to develop the next generation of applications, system integrator partners. We're looking for collaboration for research projects. So with that, I'll hand it back to you, Ivan.
Thanks a lot, Nazanin. This was really great to see that photonics is going to be the future for a lot of new markets and applications. I had a few questions, but I would like, I prefer first to go to the questions we have from the audience. And actually one of your partners, if I'm not mistaken, according to the last slide from VPI Photonics, Chris Maloney, has a question for you. Chris?
Yeah, hi Nazanin, good to see you. I liked your point about having these vertically integrated, I guess, market, and you're trying to transform it into a more horizontally integrated to allow more people access. So I was curious, how does that relate to the applications for the PICs that you're seeing? I would think more datacom, telecom companies are more vertically integrated, or maybe you're seeing more startups accessing the foundry, since you're enabling pretty much anyone to enter your foundry. So I'm curious what types of applications you're seeing, and you know, what are you seeing more of or less than? If you could comment on any trends there.
Absolutely. So in terms of markets, we obviously see the communication, the telecom, the datacom. We see sensing, LiDARs pretty hot. We see quantum computing. But it's not just startups that we're enabling. We have large companies coming to work with the JetX industry consortium, with SMART specifically also, because they are seeing the value in terms of how the partners are supporting one another. We are working with some Fortune 100 companies, so it's really all over. But real terms of the industries is the ones that you probably see and hear a lot more of: the telecom, the datacom, the LiDAR. This is definitely the forefront. I think the quantum computing is what we'll probably see in the next 5 years a lot more of. At this point, it's definitely the startups coming to us.
Okay, great, thanks.
Okay, thank you, Nazanin, for the answer. Yes, and actually, I had the same answer. What do you think that will be the first adopter with massively produce? And I think you already gave the answer to Chris. And we have another question from Chilas, Dimitri Geskus. Please.
Hi. Nazanin, thank you for the nice presentation. I've got a small question about the Aspire project and the WIPE project, especially. That I see it now for a second time passing by, that you transfer print components onto a wafer and then make a hybrid integration on large volumes. What will it be? What timeline would you think that this becomes readily available, so I can order a batch of populated wafers in the future?
I think Martijn can better answer that, but right now the fact is that we can create a PIC on indium phosphide for you, and it's just a matter of which portions or what kind of components you want, and then you can have your PIC of passive platform that you want to be transferring it to. What timeline? I don't know, Martijn, if you can comment on how mature this technology is. I think it's a matter of what is the passive platform you're looking at right now. I imagine the active is definitely indium phosphide. We know we can manufacture it monolithically, so it's a matter of what you want to transfer it to. Now, how well can it be transferred using the coupons? I think I'm going to bounce it back to Martijn if he is available to answer that.
I will get in contact with him. But then also about the WIPE project, where you also have active electronics involved there. And yeah, I'm making very simple lasers, and sometimes we need feedback of them, and then we need a bunch of electronics around it. Are there some pilots already running with electronics embedded on the wafer scale, or on ready for high volume production? Some pilots?
So it depends what your question is about high volume. Are you talking about wanting to do pre-volume to test the market? Because high volume means something different. What TRL level are you looking at?
I think it will start off with pre-volumes. I think I like that term. So yeah, so.
If you're looking at a TRL 4 or 5, I definitely think that's something that would be feasible. It's definitely been done, and we're definitely able to do it, I believe.
Okay, yeah, cool.
Okay, great. Thank you. And we can, of course, bring you in contact afterwards, so you can continue the discussion. I will have a few questions. I really want to ask, sorry already, from Amir and Andreas, but we only have space for one more question. So I will go to Ivan Davis from AMQE.
Hi, thanks, Ewan Davis of IQE. Hi, thanks, Nazanin. That's great talk, by the way. You talked on your hybrid integration roadmap about putting an indium phosphide photonics wafer with a silicon photonics wafer. Is there an ideal wafer diameter that you think you would do you think is most optimum at the moment for indium phosphide to go with silicon? And do you think even at pilot level you're there yet, or is there some way to go before you get the optimum matching?
So if you're talking about having a fully matched wafer to wafer, obviously for indium phosphide, the dimensions of it is not getting close to what can be done on silicon wafers.
That's right.
The difference is quite a bit.
So are you working at 4 inches in the pilot line at the moment, or even lower?
So I believe the example I had wasn't silicon, it was silicon germanium wafer. I don't recall the dimension for it, but for indium phosphide, it can't be more than 4 inches at this point. So we'll have to match the 4 inch with 4 inch of another platform.
Are there limitations because of the mismatch in diameters, or does that not matter at the moment?
That's a good question. Limitations because of the mismatch of the diameter. I can come back to you on that.
Yeah, great. Thanks. That'd be brilliant. Thank you very much. Well, thanks anyway.
Sure.
Thanks a lot, Ivan. And Amir, I'm really sorry we have to go to the next speaker. So please stay for the after party session. I would like to go now to Geiselmann from LIGENTEC. Oh, you're ready, Mikael. Thank you. The floor is yours.
Yes, thank you. Thank you very much. So we are one of the third pillars. We have silicon indium phosphide, and we are doing silicon nitride, and that provides very low losses, very low propagation losses on the waveguides that is needed for several applications, and we scale that from prototyping to high volumes. Originally, we are based in Lausanne, Switzerland, but we have a global reach of the customers that we're serving, and we provide low loss silicon nitride integrated photonics. Our offering is that we do what we call the all nitride technology, where most of the light is confined in the waveguide of the silicon nitride, which gives access to very low propagation loss, very small chip sizes, and also very high power that you can put in those waveguides. So there we have measured up to 10 watt in the waveguide, which is important, especially also for applications such as LiDAR. And we see that the nitride technology, kind of an extension to the silicon photonics, where we can reach from the visible to the mid infrared with very low losses and very high power propagation. Our versatile PIC platform offers several process modules at different thicknesses for different wavelengths operations, and that comes together with PDK, with standard passive building blocks that are integrated in all the software providers that are listed here. So our offering is that we can go from R&D and prototyping. We have MPW offerings to custom PIC developments, and through the partnership that we have with X-FAB that we announced last year, we have also the capability to bring that to high volumes in a fully automotive qualified CMOS fab, which runs 24/7. In the end, we deliver photonic integrated circuits for next generation products. And in terms of hybrid integration, where we see silicon nitride playing a role, and this is what Martijn already nicely introduced, is that we use, for example, the low loss of the silicon nitride for the application you need, and then wherever you need to put an active material, as silicon nitride is a passive material, wherever you need to put an active material, you put that locally. So the whole idea is that we have developed the PDK for silicon nitride, and we do not want to redevelop now a PDK in another material platform, but rather use the PDK that we have in silicon nitride and add the materials where it's required by the application. For example, a laser, a modulator, and so on, what we already have heard in the two talks. And there's different ways of wafer level integration. Also, that was already mentioned by Martijn. There's monolithic integration, wafer bonding, or microtransfer printing. And just to put that in perspective, so on the left we have monolithic integration, which is scalable, and here the initial cost is probably the most prominent one, but once in volume, then the cost drops dramatically. Whereas if we go to the very right, to have hybrid integration, where you put two chips together, there the initial cost can be overseen quite good, so that it's a minimum initial cost, but that's not really a scalable process if you go to the millions. And heterogeneous integration, there you take, for example, an indium phosphide wafer, and you take the laser part. So you don't do wafer bonding of indium phosphides to silicon nitride. You do the laser part or the modulator part, and puts that in the location where you need it in your silicon nitride chip. And with that, you have the best of two worlds. You have the very low loss of the silicon nitride in combination with laser material or modulator material. And here just a few pictures how that looks like. Hybrid integration. What we call hybrid is, for example, a butt coupling, where you package an indium phosphide chip, in this case an SOA, to the silicon nitride chip. So you use the silicon nitride chip if you need the very low losses, and the indium phosphide chip for as a laser material in that case. What we call heterogeneous integration, we also have examples there. So this is rather, you take the wafer of silicon nitride, and then you put in one case, for example, lithium niobate, where we do chiplet bonding or wafer level bonding of lithium niobate onto the silicon nitride wafer. And here what is nicely described in that picture here, you can transfer the mode partially to the lithium niobate and get access to the properties of lithium niobate, for example, for fast switching or second harmonic generation. But our vision is that you put that only where you need that, and have the PDK with all the high Q rings, AWGs, all the passive building blocks in the silicon nitride. I think that's an overview of what capabilities we can see in the near future in terms of modulation, active integration, also with photodiodes, if it's either indium gallium arsenide or germanium photodiodes that can be heterogeneously integrated in silicon nitride. With that, I would like to thank our team and also advertise that we have open positions, and I'm happy to answer any questions. Thank you very much.
Thank you, Michael. Thank you for the great talk. In fact, I have a question for you. I'm wondering, so silicon nitride is, of course, a very perspective platform. However, in terms of material, do you face any problems with finding good silicon nitride material? And also, in general, what is your plan for the scale up Because maybe you can tell us a little bit about your partnership with XFAB.
Yeah, so the scale up is that we have our process transferred to XFAB, and we can we don't see volume as a critical problem anymore. In photonics, the volumes we're talking about, at least in the next 5 to 10 years, that is well below electronic market volumes. And here with having a partner that is running a CMOS fabrication site, we don't see that the volume is blocking us. And in terms of material, that is part of our core identity, that we care very much of getting very good silicon nitride that provides very low losses on the chip.
All right, that's very clear. And Nick from QVIL is wondering how transparent is the scale up from the MPW runs to the XFAB production, so full scale production.
Probably can. What do you mean with transparent? What is?
I guess. What are the challenges that you see in this?
I mean, for all the MPW is a great tool to try out the technology and to get the feeling of where to tune or to have a small number of devices. And then once you scale them to a pilot or volume production, then you do a process freeze, a design freeze, where nothing is tuned anymore, and that's when it then runs at the volume fab. I'm not sure if I got the question right, but.
Yeah, it's Nick here, right? That was kind of where I was going, and I think you answered it in the previous question, which is the PDK is the same, right?
Yes.
Your process is the same between the two sites. I was just trying to confirm,
yes,
understand how that worked. So thank you.
All right. There is one more question from Pinas from Quant LR. Would you like to ask your question yourself?
Yeah. Yes, so obviously the power, I can read it out, or probably you can unmute yourself and ask it.
Okay, I was just curious. I would imagine one of the challenges of the integration, whether it's wafer to wafer or discrete, is the power transfer. And I was wondering if there was any particular advantage or disadvantage to any of the approaches. Which I imagine would also be a factor besides cost and speed.
Of course, especially if we're talking about power like SOAs and lasers. Where do you? I think one question is how efficient can you couple from one material to the other, and there will always be losses. And then how do you deal with these losses? Where does that energy go that is lost? And there is also several approaches how to deal with that for the different integration paths, be it hybrid, monolithic, or heterogeneous integrated. And here probably the easiest is probably the hybrid approach, because there you can really fine tune with from the packager side, but the scalable approach, that is where everybody wants to go, and there's definitely still challenges to overcome.
Thank you.
All right. Thank you, Mikael. Thank you for telling us about the platform you're using, and obviously combining silicon nitride and indium phosphide is the most exciting part, and which as it leads to making very special devices. And there is one person in the room, Dimitri Geskus, the CTO of Chilas BV, that could maybe tell us more about this. Dimitri?
Yes, I think you can hear
like
me.
to start your presentation.
Yeah, oh yeah, okay, we'll go to the presentation.
Right.
Okay, there we go. Screen. Go.
Okay, we have it.
There we go. Hey
Yeah.
guys, nice meeting you, and thanks for the introduction, and thanks for the speakers before me, because they gave me quite some footage. So I'm from Chilas. Chilas is a fairly new company, I must say. We spun out of LioniX International in 2018, and at the end of 2018. And well, we have the main office in Eindhoven and the laboratory space here in Enschede, close to our close collaborations, our neighbors, LioniX International, where we get our silicon nitride chips from, and very close to phix photonic assembly, where they do our high volume, fully automatic assembly of our laser systems. And we've got Quicks around the corner, which always have intriguing questions to us, how to make the laser more neat and for the application. So yeah, this is basically our ecosystem here in Enschede. And yeah, well, we commercialize ultra narrow line with external cavity lasers. So as explained by the previous presenters, is that they've got a small indium phosphide gain section, which has the advantage of generating a lot of light. And we've got silicon nitride, which has very low losses. And well, when combining these two effects, you get a very nice laser systems. And so the indium phosphide provides the high output power, and the silicon nitride, due to its low loss and the ability to tune some sections on the platform, we can make filter circuits which are based on two rings which are set in Vergyris, and I'll demonstrate a little bit about this. Is that we can tune the laser wavelength to feed back to the gain section throughout the full C-band and even beyond there. So yeah, the product is very simple, although I must say the thing it does, the fairly high output power and the narrow line width is giving rise for many very complex applications which we can drive the system with. So the gain section is butt coupled to the external cavity. And well, these are already explained. We have the two rings that make the laser tune to basically any wavelength you want to address. We've got several products, few standard products. We've got a fixed wavelength application. It is tunable, but it's specialized for driving one laser at low power consumption. And we've got a tunable application, which has C-band, but I will show you in the next slide that we can also go far beyond that C-band application. And we have a piece of electronic driver, which yeah, really takes the best out of this laser concerning high output power and tunability and the low noise. The lasers are very sensitive to electronic noise, and I must say there's a lot of development going on in making the electronics, driving electronics, as low noise as possible. Meanwhile, we're also making a piece of software, a tuning software that fully automatically controls the lasers. All the lasers need to be calibrated to fully exploit this feature, and this is typically what a consumer would love to see: is two buttons, one button power and the other one wavelength. And yeah, we're developing that the product for the customers. Yeah, here are some specifications, some specs that we reach. I start with the boring parts, that the side mode suppression of other modes, laser modes or spontaneous emission modes are super suppressed. So we've got a side mode suppression ratio of more than 50 dBs. Relative intensity noise is also super low, thanks to the larger cavity, and yeah, so the laser is super stable and yeah, super pure light. we can tune it. So in this example, from 1480 to 1600 nanometers. And around this wavelength band, it gives a fair output power of up to 40 milliwatts. And I think this is driving a lot of application. Most recent developments are concerning together with scientists making electronics for feedback in France, and they measured the line width of our laser, which is approximately 4 kilohertz, or even sometimes a bit lower, depends on the electronics and the cavity. And they managed by using a feedback mechanism to suppress the phase even further to record low. And I hope to publish these results soon. And a little bit of development in the far future or near future, I must say. Things go very fast. So I would like to extend the SCL band a little bit beyond the 1600 nanometers in half a year from now. At the moment, we go up to 1600 nanometers, but next run is in progress right now. So I hope to go beyond that level. Near infrared lasers are currently in the lab operational. Visible lasers have been demonstrated, and thanks to the silicon nitride, which is transparent for all these wavelengths, give us a gain section, and we'll make the appropriate cavity for it. So that's the strength of this platform. In mid-2020, I hope to have lasers in a compact 14 pence butterfly housing available with 2 gain sections. We expect to have a little bit more than 100 milliwatts of output power in the fiber. And I think we can squeeze a little bit more power out of these devices. We will see in the real time. So I hope in a few months to have it on the website. And on top of that, we have some devices where we have some structures where we can track the wavelength, so you can get feedback from the laser to see at which wavelength it is. And it's always nice to have for some OEM applications. Well, and now, as I highlighted, any wavelength on demand. Give us a gain section, and then we'll go. And if you don't have a gain section, we will find some gain sections there. Yeah. As explained, the applications are for a wide range of applications: fiber sensors, LiDAR, of course, coherent communication, OCT, microwave photonics, spectroscopy, atom cooling, quantum computation. All these applications now pop up, and they all need specialized, high pure wavelength laser sources. And I think we can do that for all these applications. This is our presentation in a nutshell. Open for any questions. Thank you for your attention.
Thank you, Dimitri. Thank you for a great talk. And these results are very impressive. Actually, I have a question. Do you see any room for improvement, for further improvement? And with regards to that, can EPIC members do something for you?
Yeah, so improvement is always there. As indicated, is that the line width is narrow, but you need very low noise electronics to really exploit that. One of my colleagues at LioniX told me it's like a race motorcycle, but sometimes the driver is drunk, and that's what we now do with internal referencing. I think in a year from now, we should have an internal reference, a gas cell, something like that, implemented into the gold box. And then we can make the driver not drunk anymore and really have very, very nice performance of the laser. The output powers, yes, 100 milliwatts. If it's 300, people are getting more happy with that. And what we would like from the EPIC members is that, especially in this hybrid integration, what we're discussing here, is that we would like to currently put on photodetectors for biasing and monitoring, but it would be nice to also have some feedback directly on the chip to the laser performance itself, to trim the wavelength or stabilize the wavelength, and also to expand the colors and the bands. We see that in the world people are presenting silicon nitride structures that can even go beyond the wavelength ranges I just presented. And there we need just gain sections providing a wider range, or perhaps multiple gain section arrays that can be flip chipped with the transfer printing, which has been discussed here. So this is definitely something where we need EPIC members. We can't do it all by ourselves. So yes.
All right. Thank you very much, Dimitri. As we're speaking of the combination of silicon nitride and indium phosphide, there's actually one more person that could make an input on this topic. Christian Koos, the CEO of Deep Light AI. Would you like to share something?
Yeah, can I just share my screen?
Please go ahead.
Can you see my slide?
It's coming. Good.
All right. So thanks, Dimitri, for pointing out all the advantages of silicon nitride in combination with 3-5 gain elements. Then I don't have to repeat that. I mean, our approach is actually fairly similar. So we use to build external cavity lasers. You can see this on the right. We have 3 through cavity circuits. As Dimitri just mentioned, they are broadband transparent, so we can build these lasers at any emission wavelength through the visible and the near infrared. They are low loss, the silicon nitride circuits, so we have ultra low phase noise, sub-kilohertz intrinsic line width, and in addition we have highly agile tuning actuators based on piezoelectric materials, and with that we can tune the frequency of the lasers fairly fast. Typically over a gigahertz. You can see here at the bottom a typical triangular tuning curve, which has an excursion of a little more than a gigahertz and repetition rates of up to a megahertz. And those things are obviously very useful for FMCW LiDAR. So that's our lead application that we are focusing at the moment. But they can also be used in fiber sensing, test measurement equipment, quantum optics, and so on. So what we are looking for, and I kept this very short because I was told I only have 1 minute. So what we are looking for is lead customers and development partners that are in need of compact, frequency agile, robust lasers that have very low, so very small line width. And as a parallel activity that I don't go too much into detail about, we have also built up a thin film lithium niobate integration platform that we are currently opening up through multi-project wafer runs. So the first run will be in autumn, in September. If you want to know more about that, you can follow that QR code. That's also something that we offer. Thanks. It was a little more than a minute, but I think it's okay.
Oh, no, you're good. You're good. Thank you. Thank you very much. Thank you very much for this addition to the topic. And I think there was a question from Amir from CSEM.
No, actually, I think I in a mistake, but actually now, so Christian, thank you so much for this very nice sort of presentation. So I'm actually wondering about the power consumption of this piezo-based tuning, compared to, I mean, both LNOI, which I think it's obvious, but also the thermal tuning. Can you comment on that?
I mean, the thermal tuning is obviously fairly power hungry because you constantly heat. For the piezoelectric, actually, it depends a little bit on what material you use, but in essence, you're just charging and discharging a capacitor. So you don't have any current flow, so the power consumption is not an issue. For the thermal tuning, that's simply, but that's an issue on silicon nitride in general because of the low thermal optic coefficient. That's why for fast tuning, we rather rely on piezoelectrics here. And compared to LNOI, it's more or less comparable. The voltages are a little bit different, but it's a capacitive load in both cases.
Okay, thank you.
Okay, Wilfred from SUS MicroOptics.
Yeah, thank you. Actually, I had a couple questions. So for Chilas, so you used an external sensor, Dimitri. Can you use this sensor as an external chip, photonics chip, for your feedback loop or for tuning your wavelengths? Could you use that chip as an actual sensor to be extremely sensitive and very fast? Because I could imagine that it's very sensitive to the environment if you design it like that. I mean, obviously you probably make it more robust in your system, but
So I think it's a very good question because yeah, that's also what we're looking at. You want to finally have a feedback system on your interface that you can control wavelength and power in one go. So at this moment we have the chips equipped with a small power tap, so fraction of light goes to another side, and then there is just a Maxino interferometer which makes a wavelength discriminator, and then some grating couplers and a flip-chipped photodetectors on top of that. These things go up to 10 gigahertz speed. We don't even have the infrastructure around it to read out with that speed, but for DC application, it works fine. I think in the future, in the near future, we might have to go to much faster detection on top of the triplex chip, or yeah, the silicon nitride chip, where we have some feedback, for example, to do the trick on wavelength stabilization. And yeah, I hope to have the first results ready in next year. And a project has been filed to develop that part, but that's ongoing. At this moment, we do it with off-the-shelf equipment for stabilization.
Yeah. Okay, well, that's a great idea. Okay, thank you.
Yeah, thanks for your question.
All right, thank you very much. So we've jumped onto this silicon nitride and indium phosphide topic right from the beginning, but let us switch gears for a second, as we forgot to discuss what silicon platform can offer us. And I cannot think of a better person to give an input on this than Alan Delpy, the business developer of Soitec. Would you like to share something with us?
Yeah, okay. Do you see that?
All right.
Yeah, you see my screen? Okay, great. So yes, the beauty of silicon photonics is clearly that it's now capable of making interesting things based on SOI. So starting with the wavelengths, we understand that silicon photon might be opaque or transparent, and that results in for photons in two kind of applications. The first one is imager, based on very thin SOI, even with multi-stacked SOI, addressing the composition of image sensors. And the upper level is where the silicon starts to be transparent. And here we are addressing what we name silicon photonics, where you can pattern the top of the wafer with creating waveguides. With our technology, we can even make some interesting supply of 3-5 wafers based on smart cut technology. So for the application with silicon photonics, of course, laser is not something that is inherent to silicon photonics. So now we see that heterogeneous integration is feasible, and there are many players coming with solutions, enabling to have a free air or optical fiber interconnect, addressing consumer market or automotive market with a spectrometer or LiDAR. But of course, for optical fiber interconnect, we see that transceiver CPOs or optical IOs are now starting using massively this solution with different kind of integration with modulator like MZI or microring. So the key challenge for silicon photonics is to understand how far we should go with uniformity of the top layer and the defectivity, enabling to have different kind of applications. And I guess the next speaker will show one of interesting application. Of course, the side, which is sitting underneath the top layer, is enabling to have the index, which enable to really to create with a cladding on top the waveguide. But not least, last but not least, the bulk could be used as well to for the interface of the fiber, And we are challenged a lot with the quality of the bulb to make a sort of V-grooves enabling the fiber integration, or definitely TSV integration. And all those are fully available in 8 and 12 inches in large volume. So today, clearly with silicon photonics, we have already started tens of kilo wafer every year in mass production. Thank you, Ivan, for.
All right. Yeah, thank you very much, Alan. So, I mean, the SOI platform is definitely one of the key pillars for whole silicon photonics. However, what are there plans for introducing new Soitec products that are maybe based on lithium niobate on the insulator, or other materials that could be interesting for photonics community?
Of course, we are observing different kind of platforms, starting from silicon nitride, lithium niobate, but not only those. Also the integration of indium phosphide at a much larger scale than 4 inches. And we have different plans that I can't comment today, but we are deeply following possible heterogeneous integration of those platforms on top of silicon. And clearly we see some foundries that are today offering some interesting path to multiply the possible options of integration.
All right. Yeah, thank you. And obviously there is one company that is already using these technologies, the heterogeneous integration of 3.5 and the SOI platform, and that's SCINTIL Photonics. And Yannick Paillard, the CCO of this company, could share some thoughts with us. Please go ahead, Yannick.
Okay, sorry for this. Can you hear me?
Yes, it's good.
Yeah, okay, perfect. Good afternoon, everyone. Thank you, Ivan and EPIC, for giving SCINTIL the opportunity to present our augmented silicon photonic technology, which is enabling monolithic integrations of laser for large and high growth markets. So I'm Yannick Paillard. I'm at SCINTIL. I lead the business development activity, and I'm happy to be here today. And please excuse my voice and possible cough. I'm just recovering from a flu, and I'm a bit busy, but I will do my best. So maybe in a few words, introductions of SCINTIL. So we are a fabless company. We are developing and manufacturing silicon photonic circuit with integrated laser. Company was created in November 2018. We're based in Grenoble. We have as well offices in Toronto that we opened up in January. We raised 4 million euro in 2019. So we are a private company with private venture capital, French mainly today, and we're working on the second fundraising. The core technology originated from CLAT after 18-20 years of R&D, focusing on silicon photonic laser and this molecular bonding. This is something which is of great expertise of CLAT, and we have a portfolio of but more than 20 patents that we licensed, and some that we have been developing on our own. To reach the mass volume that we are aiming for, we have been reaching some manufacturing agreement with commercial foundry and industrial partner in Europe, and as well elsewhere for the foundry, which I won't disclose, so don't ask me. And we have early product development engagement with 3 major customers covering telecom, datacom, and high performance computing. Talking about the technology, our technology combines the best of what we call the silicon and indium phosphide photonic. I mean, with the integrations that is called box-on-box, which leverage, and we insist on that, commercially available silicon photonic platform. If we had to summarize our integration process, we can summarize it in three steps. First step, we process the silicon photonic device in a commercial foundry using the standard silicon photonic platform. Then we have this operation that we call handle exchange in order to flip chip the process wafer on a new silicon handle before we can come and bond small pieces of unprocessed 3,5 indium phosphide material on the backside of the wafer, and only when it is needed. So this operation is called die-to-wafer bonding. And then we go back into the foundry to complete the laser or SOA fabrication with a CMOS compatible process. And the resulting products is obviously a fully heterogeneous integrated PIC that combine all the silicon devices that are available on the market or that you can have on the market, plus the laser and the SOA. So if we, here is a cross-section showing side by side a standard silicon photonic device with an augmented silicon photonic with integrated 3.5. The standard silicon photonic usually use, in fact, a thicker box, whereas we leverage a much thinner box on our process. The silicon photonic device on the SCINTIL process are upside down because we flip the silicon photonic wafer after the step one. And like for the silicon photonic only process, all the electrical contacts are coming on the top, meaning that TIA and modulator driver can be flipped on the top of the PIC, or the PIC can be flip chip assembled on a substrate. And fiber coupling could be either from the surface on the edge. What we deliver to our customer is a full package of item, because again, we are not selling any end product. We are focusing on selling PIC only, but we are delivering evaluation board to assess the performance of our PIC, so in the form of evaluations package. And then after we are working on reference design implementation of this PIC, looking at delivering the firmware for that runs on the standard MCU. We as well focus on interfacing with standard high-speed electronic IC and TIA, whether they are standalone or integrated. And we have as well developed a patented fiber attachment scheme for aligning the fiber array with the PIC. And obviously, we deliver the PIC for mass productions. The market that we are targeting is primarily the high-speed optical communications. We address both what we call the historical requirement of data center, which is today 100 gigabit per lambda, and we are focusing on 800 gigabit as an entry point to the market. And obviously, we are working as well on the 200 gig per lambda, which we believe will come in 2024, as well as the emerging requirements of cloud computing driven by the so-called CWDMA MSA for multi-wavelength laser source. And leveraging what we do into the optical communications, we have as well some R&D activity on the FMCW LiDAR, because we believe that the integration platform that we deliver for the optical communications can have as well a great advantage for LiDAR applications, whether it is for integrating the laser or for integrating the SOA. To answer some of the questions that we keep on asking in the EPIC meeting, what we're looking for, we have been working on quantum well integration so far, and we believe that quantum dot could be of interesting advantage as well to add to the platform. So we'll be happy to collaborate with any AP provider that have content adopt. And we have as well some growing challenge going with the increase of speed of the baud rate, looking and finding drivers that either are in quad or octal configurations to drive our either Mach-Zehnder or ring modulator. So that would be something that we'll be happy to discuss. That was about all for the introductions. And obviously we are a growing company. We are hiring. We are sitting in a great city, which is Kolgodam, in the middle of the mountains. I'm going to be doing a bit of advertising of where we are, but because it's a great place to work as well as the great place to work at SCINTIL. Thank you. That's all for the presentation. I'll be happy to answer your questions.
Thanks a lot, Yannick. Thank you. I hope you're doing well. So I don't see any question for the moment, but I would be curious to listen if we can escalate this one in more materials and this the same technique that you presented before.
Sorry, you want me to?
If we can have additional platforms, if the technique that you explained, no, the indium phosphide on silicon, you can think of having something more.
What we see is, like, for example, today we are using indium phosphide as the substrate to add the quantum well. I mean, if there were another material that would be that we could be considering other material to bond on the backside of the wafer, but that's where we need to do some experimentation, because today most of our experiment has been with bonding AP on indium phosphide substrate, and this is where we are standing. And maybe, but the question was maybe not this one. You were asking me whether we would
we could dream of thinking adding even more materials than one, no? So we can always
adding adding 3.5 with silicon photonic is bringing is already bringing a lot of the things that has been presented so far. So if I heard Martin at the very beginning of the presentation, he was saying, well, it would be great if we could have silicon nitride, if we could have laser, if we could have a passive, all of that, we can integrate that on our platform. And obviously there is always after better material to do this and this, but let's start to have that as a mass producible platform, and we'll be happy with this.
Okay, yes, I agree. Thank you a lot, Yannick, for the answer. There is one more question that comes from my colleague, Tracy Vanek.
I think I'm unmuted. Yannick, very nice to see you again. I have two questions that are a little bit related. Hi. So the first one is, where are you are you in sampling? Do you have products out, or where are you in the production at this point?
We are in a prototyping phase of, I mean, we have a first step, which were to prototype everything in an R&D fab, and we are coming to an end of sampling product out of the foundry. So into an industrial line, to have sample out of a production line. And this is, so we have been having sample for, not sample, engineering sample since the mid of last year. And we should be completed our process of characterizing our industrial flow by end of this year. So we'll have, we have already completed some major step in Q1, and that's why we made this announcement at our FC, and we will have a major step in June this year, exactly, which is something important for us, which will be the integrations of all the features, including the laser. And then after, we are looking at engineering sample to customer in Q1 2023, so in about 9 months from now.
Excellent. And I wanted to ask you too, so you have this unique process where you flip the wafer and then you add additional pieces onto it, if I have that correctly. Could you possibly add different types of pieces onto the wafer if you needed to, like to create multiple different samples for different clients, perhaps? So would you be able to do, you take your base wafer, you flip it over, you add the elements onto it. Could you add different elements onto different areas of the wafer?
Yeah, we can have different, I mean, for example, if we have to create a CWDM4, then we will add 4 different elements of 4 different AP in order to cover the full range. But that will be 4 different elements of indium phosphide going on one design. I don't know if it was what your questions.
I was thinking if it could be a little bit more creative, so that if you were running prototypes, if you could run like on the same wafer, different prototypes when you flip over this wafer and put different pieces in different areas. Is that possible, or are you really looking to have something uniform for the production?
We're looking for production. We are not, again, the whole purpose of what we do is to go for volume. So we're not, I mean, the prototyping was before, and we're not looking at having different prototype on the same wafer. If we do so, that will be with the same epitaxy in that case.
Okay, great, wonderful. Thank you so much.
Thanks a lot. Thanks a lot, Yannick. Thanks a lot, Tracy. And no more questions. So I think it's a good time to go to our next speaker, which will start a little bit from the other side of the pitch, which will be on packaging. And I would like to ask Moritz Kleinert from HHI to share his screen. And then the floor is yours, Moritz.
Thank you.
There we go. We see your screen.
Perfect.
Perfect.
Yeah, thank you very much for the introduction. My name is Moritz Kleinert. I'm with Fraunhofer HHI in Berlin. So we are an RTO working on photonic components mostly for telecommunications, but also for a broad range of applications over the last years. We do have our own cleanroom facilities where we fabricate mostly indium phosphide components. We are also part of the JAPICs pilot line that we heard of in the talks of Martijn and of Smart Photonics earlier today. So we fabricate monolithic integrated circuits, also separate components, lasers, detectors, modulators, whatever you can think of in indium phosphide. However, we also do have dedicated hybrid photonic integration platforms. One of these is based on polymer waveguides, because today we heard lots of the reasoning why hybrid photonic integration is useful, especially for certain applications where you have to do, otherwise you would have to compromise between the performance of different building blocks. And maybe today I will introduce quickly what we do in terms of this hybrid integration. We do not only integrate indium phosphide with our polymer waveguides, but also other semiconductor material systems such as gallium arsenide for shorter wavelengths. For example, we couple SOI, lithium niobate on insulator, and also silicon nitride. And on the other side, one aspect of hybrid photonic integration that is often overlooked is the integration of micro-optical elements into photonic integrated circuits, because lots of functionalities that you can do in free space optics today, you cannot efficiently transfer to integrated optics. So there, the use of micro-optic elements on the chip may provide a solution for that. And I will briefly introduce just 2 examples here. One PIC is a QKD transmitter PIC for BB84 coding. in order to realize secure communications, and the other one is a transceiver PIC for passive optical networks. And these were realized using this toolbox approach of the platform with thin film elements, butt-joint coupling of actives, coupling of photodetector arrays via 45-degree mirrors, and ear grooves for the micro-optical elements and passive fiber attachment, as well as highly efficient thermo-optic components, because the polymers have a high thermo-optic coefficient and a very low thermal conductivity, in contrast to, for example, silicon nitride. And yeah, maybe 2 or 3 examples from functionalities that we can realize there. First is also tunable laser, hybrid laser, similar to the approach that Dimitri has shown before, with an indium phosphide gain element. In this case, it's a Bragg rating, realizing the other facet of the laser. And in the example of the QKD transmitter, there the tuning is not that important, but what is critically important here is that the lasers are indistinguishable. So we have 4 lasers on the chip, and all of them have to be indistinguishable. So you really need to fine-tune them to realize that. On the other hand, for example, for colorless operation of the transceiver passive optical networks, we can realize the 20 nanometer tuning in order to address the DWDM channels. And the beauty of the hybrid integration concept is now that by exchanging this indium phosphide gain strip, for example, for a gallium arsenide gain strip, we can use the same concept and realize tunable lasers at 1064 nanometers and even shorter wavelengths at 785 nanometers, and combine this with all the integrated optics and all the elements of the toolbox that are already developed. Other elements of the toolbox, for example, are these thin film filters. As I've said before, in free space optics, you do filtering mostly by dielectric layer stacks that you deposit, for example, on lenses or on mirrors. In integrated optics, this is different because you do not have any facet that you can coat. What we have developed is these kind of use of thin film filters. These are just 10 micron thick polymer filters with the dielectric layer stack coated on top. So you can use the very same dielectric layers that you use in thin film in free space optics, and integrate them on the thin film filters on wafer scale and insert them into edge slots on the wafer, for example, to realize highly efficient polarizing beam splitters and half wave plates for the preparation of the qubits in the QKD transmitter, and to realize the up and downstream dichroic mirror for the C and L band in the transceiver for passive optical networks. And a third example that is that showcases the integration of micro optics with integrated optics in a hybrid way is the use of U groups. In this case, for classical communications, we use it for the passive fiber chip coupling of single mode fibers. So what we do is we precisely etch these structures on the chip so that the waveguide of the fiber is directly opposite the waveguide of the chip. And the precision is of the single mode fiber coupling is being provided by the chip itself and not by the assembly technology. And on the other hand, we can also move this on the chip, for example, to realize on-chip isolators. So we integrate GRIN lenses, graded index lenses, that collimate light from propagating in the waveguide. The light propagates through the free space section and is then again on the chip coupled back into the waveguide. And into this free space section, we can integrate basically whatever we like. For example, non-reciprocal, non-linear optical elements to realize, for example, these very highly efficient on-chip optical isolators. We do not only do this on optical benches, but we also think about how we can scale the assembly processes together with our partners, for example, ficontec, which is one of the sponsors of today's workshop. We have one of their machines installed in our labs and are closely collaborating with them in order to automatize these hybrid assembly processes. And yeah, with that, I would like to conclude my talk. We are always open for cooperations in projects and commercial cooperations. So we have close cooperations with lots of the companies and RTOs and research institutes that have talked today. And we are always open for more. So thank you very much.
Thank you very much. Thank you very much, Moritz. Let me see if there are any questions in the room. Please raise hands to ask a question to Moritz. And well, actually, yeah, I think Fraunhofer SHI is a very important partner for many people in the room, and is a very active member of EPIC. Do you maybe have a specific needs from the other EPIC members that that you can announce, Moritz?
Well, as I said, we as an RTO, we are interested in joint research and development projects with partners based on our indium phosphide technology, based on the hybrid integration technology. And also we are happy to go into direct cooperations with potential customers. And one thing that was mentioned today already is the integration with electronics. I think this is a very important point that is often overlooked in the development of the PICs themselves. So in the end, we want to sell things. So we as a community want to sell things to end users that usually don't care whether it's photonics inside or electronics or some other fancy technology, but it has to work. And I think to think this from the design of the PIC, manufacturing of the PIC, and the integration with the electronics and also the software, this is to me the most important point.
Okay. Okay, thank you. There is a question from Dove from LioniX International.
Yes, please.
Hi, Moritz. Thanks, nice presentation. What is the power level that you can handle on your platform there, especially when it comes down to lasers?
Yeah, so at 1550 nanometers, this is around 20 dBm on the chip in a single mode waveguide. So yeah, roughly that.
And for visible wavelengths or lower than?
We haven't done extensive tests at these wavelengths yet. But I would say that probably down to 800 nanometers, it should be in the same range. And then there are other defect mechanisms, mostly at the facets, probably.
Okay, thanks.
Okay, thank you very much, Moritz. And with this, I think we're coming to one of the last topics of the meeting, which is packaging. And I couldn't think of a better person to present it than Jeroen Duys from phix. Jeroen, would you like to share your thoughts?
Ivan, there was one, sorry for interrupting, I'm really sorry for interrupting, but there was one more question from Andreas.
Yeah,
Right,
just
yeah, Andreas,
sorry
I'm really sorry.
Go ahead, Andreas.
Thanks, Panas. Maybe not directly a question to Moritz, but I was wondering, when we have seen the roadmap towards integration, that Smart has presented, also Martijn has claimed, we are somehow on the path from hybrid integration over heterogeneous to heterogeneous integration and maybe even monolithic integration. And given that we have, Intel and TowerJS have shown that the heterogeneous integration is really working on a commercial basis. However, most of the talks today, and I think most of the European ecosystem is working on the hybrid integration scheme. So I wonder, where do we stand, in Europe with respect to moving towards heterogeneous integration, more like, wafer level integration of 3.5s with silicon photonics. We've seen the SCINTIL, approach. That is certainly one contribution here in this podium, but I would like to, kind of ask a provocative question to all of you. Where do we stay? Don't we stay too far behind with the heterogeneous integration when we still focus so much on the hybrid integration solutions?
So maybe one thought from my side. I think that probably it's not doing one thing or the other thing, and there's a natural progression from hybrid to heterogeneous to monolithic integration. But I think that depending on the application and the needs, and especially the numbers of samples that you need, there will be hugely different business cases for heterogeneous and hybrid integration. And especially if we go to other wavelengths that are not covered by the platforms that are now available for heterogeneous integration, then that is the strength of hybrid integration. Of course, if you have very large numbers of devices, then it's natural to go for heterogeneous integration. And I don't know, maybe that the focus today is on hybrid is also because the workshop is called hybrid integration. So at least that's why we focused our talks on this. But I agree with you that probably there are huge international players going for heterogeneous integration, and we have to be careful not to lose touch.
Yeah, I mean, if we have a strong, academic background and all the RTOs we have in Europe, everybody's still going after hybrid integration.
I have a question on this, Andreas. So this Twan from Synopsys, and I heard the word about cost effectiveness and economics, but isn't performance also a factor that plays here? As in that I always hear that heterogeneous integration of the 3.5 just delivers a better performance out of the box than hybrid integration because of the way better mode matching and coupling. So is it economics only, or is it also performance that plays a role here?
You're asking me? I mean,
I don't know if you can answer or somebody else, but
I mean,
but
in my
that's
view, it's always, a combination of both. Economics has to fit, but also performance has to be, matching the application, of course. And yeah, there are certain advantages in both areas. If the chips are, individually optimized, then maybe hybrid is better. If you can, just use the material and avoid losses and stuff like that. Heterogeneous might be performing better. So that depends a little bit on the application, in my view.
But especially if you talk about laser performance versus, let's say, how hard you need to drive it and the thermal aspects that then start to come into play, is heterogeneous just superior, or is that too simple to put it like that? I'm really asking questions because I don't have the answers, and I'm just curious to learn from this group.
All right. Let me, if you don't mind, let me kick in here and remind you that actually we have an open discussion session right after we finish all the talks. So if you just stay for another 15 minutes, maybe we can continue this discussion. And this being said, let us go back to Jeroen, that was about to introduce the new discussion that is more on the PIC packaging side. Jeroen, please go ahead.
Yeah, I hope you can hear and see me now. Oh.
Right,
But,
go ahead.
So I think, and it's also adhering to what Twan was just questioning, I think we are also seeing that more and more different materials are getting integrated. So I think we heard some of them already today, also like the polymers and the silicon and the indium phosphide, but we see also questions regarding gallium nitride for the visible wavelength range, gallium arsenide, gallium antimony, quantum cascade materials, lithium niobate for high-speed modulators, the same kind for lithium tantalate. So I think the discussion is not ending just for like monolithic or hybrid integration with what we have today, but new applications will also drive the demand for this in the upcoming future. So the high volume ones, I think those are obvious that people are pushing to get to hybrid integration or even to monolithic integration, whereas for some other applications, there might be no urgent need to get there because of the volumes for this new application being too low. So it really has to grow into the volume space. I think what we are seeing really is that people are really trying to figure out what are the cost advantages for one over the other. I think if you're looking to the hybrid integration, well, it's available as of today, so you can take off-the-shelf components and mix and match them such that you get a good performance and you can demonstrate it for your application space, and you can scale up if you have an urgent demand. And if you can like wait a little bit longer, well, you might be going for the heterogeneous integration, or maybe that's only like valid when your business case is getting to a certain point. So I think if you're looking to various like designs, as you see here on the screens, where we do hybrid integration with indium phosphide, polymer, nitride, and silicon photonics to build like a single module like we're doing in the Tearaway project, it's interesting to see where this will be going. So it's not just 2 chips which are combined, but it's already 7 chips that are being combined. So how to integrate that into a single chip. I think if we are looking really to like what are we looking for actually in this hybrid integration, I didn't hear anybody touching upon that yet. It's like how to make a hermetic module, since what we are seeing is a lot of the cost is being added to make like gold box structures around your photonic device to make it hermetic, since not all materials can withstand the external environment, but it's like a cost addition to your platform. And the same is for polarization maintaining fibers. Of course, we're happy to manufacture them, but if you're looking to like the cost of a complete module, that's really something which is driving. So if we can come up with solutions that can overcome the gold box requirements and also could overcome the interfacing requirements such that you can use single mode fiber, for instance, your modules would be cheaper and therefore the applicability might be a lot larger. So if there's somebody that can help out there, we would be happy to learn from that.
Thank you, Joerg. Anyone wants to reply to this? I mean, I'd like to remind you that phix is, of course, is one of the European leaders in packaging and the sponsor of today's event. So I think phix remains the reference for many of us here for the PIC packaging. And with that being said, maybe I can pass the word now to Joerg Smolenski, the business developer manager and the Nanoscribe, as Nanoscribe is developing some tools that might be very useful in this challenge. Joerg, the floor is yours.
Okay, I see my screen is on, so thanks for the invitation, giving me the possibility to talk here. So I would like to talk about our possibilities in hybrid packaging. So we are manufacturer of equipment, 3D microprinting technology based, so 2-photon polymerization. And what we try to do is to save maybe one of the main challenge in hybrid packaging. I think most of them are familiar with this. So there were mentioned coupling losses, different material platforms are used. You need to steer and form the beams between the different dies. You need to adapt the mode field diameters. And also you have issues right now with alignment tolerances. So we have very tight alignment tolerances if you do combine different materials on the same package. And so we try to propose something here which might be a solution. So we have the QuantumX Align, which enables 3D printed micro optical connections. We have a cooperation with phix. Hello, Jeroen. where we print optical micro lenses on lensed on fiber arrays. So you can see here one fiber array as a sample. So we can print freeform optics, steering optics, tapered optics, different things on the fiber array. This leads then to nice parallel and collimated beam or focus beam. That depends on what you require. Different wavelengths are possible from green up to the telecom range. And we will not stop there. We go from here's a scheme. You can see on the right side, you can see a ship with printed lens, and on the fiber array with the printed lens on the left side, a ship. So we also will go on then later on to have it printed on the chip. So in order to show you a little bit how does it work, I have a small example with a small video. So you can see here on the left is a scheme of the a green fiber array, where you see the designs here, which you want to print. And if I start the video now, I hope it's working. Let me quickly see. Yep. So basically we have a process where we detect the first fiber core, we input the second core, and then we do after this, you can see that we do some alignment. So here we detect the surface of the V-groove array and also all the emission direction in 3D, and then we print in parallel to the emission direction and vertically to the area of the surface of the V-groove. So still the alignment procedure, and this is then the printing. So we can print different lenses having a focusing or a collimating effect afterwards. So the same for on chip. So this is from the project we have handled OCD, where my colleagues are working on. You see the beam. So here we have a confocal unit instead of a camera. So we are scanning with the confocal unit the chip surface. We can detect the markers, as you can see here, these double dot squares. And then also we can print nicely and quite fast the adapted lenses in high quality to with high precision, 100 nanometer precision to the edge of the coupling elements. So this later then enables less alignment tolerances for pick and place. So you have an easier packaging process after that. This is what it looks like finally. So summarizing a little bit is we can print on fibers, on photonic chips, and also on other topographies, which is possible with the system. We have up to 100 nanometer lateral alignment. It's automatized, the printing process, and this should resolve most of the problems in hybrid packaging, like relaxed alignment or reduce the losses depending on the design of the optical elements and the wavelengths printed. Then the classical questions, what can we do for you? So we, as mentioned, we enable efficient coupling between different material platforms. And that means we can do feasibility studies, prototyping, design, and simulation for your optical interconnect issue. And finally, we do the equipment. I think that's a fair thing to say. And what we are looking for is basically challenge us with your optical coupling issue. If you have, do you need it? Come to us and ask us, and we can help. Together with Phix, we can provide you already a solution for lens fiber arrays, and others are to come. Thank you for your attention.
Thank you, Joerg. This is a very exciting technology you're developing there. I pass the word to Dimitri. Dimitri, did you have a few questions?
Yeah, thank you for the nice talk. Very interested to see this technology alive. And I wondered, I think when I looked at the videos, I think the technology is relying on a submerging in a polymer or pre-polymer environment. So you have to first soak your device, and then you write structures there, and then you flush away the non-cured components. Is that right?
Yeah, it's comparable to lithography, but we have a localized drop. It's a drop of resin, which is honey-like, basically. You print inside this resin, so polymerization is taking place inside this resin. So that's also why we have this high quality. And we can do optical quality lenses, any form you want. And then afterwards, you use IPA or PGMA to wash away the non-printed part resin.
And how do you deal with, for example, a model where there's already electronics and bond wires and everything around it?
Most of the time we don't print in models with bond wires because there's also we use microscope objectives, so there's a very slow working distance. So that's 350 up to 2 millimeter depending on the resolution.
Okay, clear.
Yeah.
Okay.
So mostly in most of the applications we print on the components and then the assembly is taking part afterwards.
Okay. Yeah. Okay. Thank you.
You're welcome.
All right. Henning, please go ahead.
Yeah. Okay. Thank you. I have one question to Nanoscribe. Are you using your own polymer materials or are they on the shelf?
No, we have our own polymer materials. So since more than 10 years, we're in the field and we have developed our own polymer materials. We have large development inside, but the system works also with SO8 or other AZ materials out there. So okay. It's a very broad range. It's an open system.
And then, thank you. And a short answer to Duis at Phix to solve the hermeticity problem for the new packaging modules. Maybe it's a good idea to talk with us about our glass platform, because using glass with electronics and micro electronics and optical waveguides in, it is quite easy or possible to make hermetic sealing using special bonding techniques, glass to glass. So we are working on that, Duis. You know.
Okay. Yeah.
Okay. Thank you.
Thank you, Henning, for your input. Yannick.
Yeah. Quick question to Joerg. It's amazing what you do with your 3D printing, but is it suitable for volume applications? Can you run volume, or is it more for?
For the moment, we cannot do million pieces, so it's medium to small volume for the time being. We're having a roadmap to improve the speed and the also wafer level processing, these kind of things. But I think we maybe can discuss bilaterally these kind of things.
Okay. Okay.
Bonne journée. Bonne journée.
Thank you, Yannick. Amir, go ahead.
Thank you so much for a very nice presentation. Actually, just a quick question. I mean, I'm pretty sure, like, you know about the other another company we are actually involved with, Vanguard Automation. So have you seen like also using this 3D printing to make these photonic wire bonds, also these macro lenses? So I'm wondering if you want to compare, your technology with them, is it like a different polymers, different wavelengths, or what are the sort of differences?
We have different polymers. The groups of the history of Vanguard, you can look up into the internet how they started. We have a couple of things patented. For example, on fiber printing is patented. We have worldwide in several countries. We have the dip-in technology to improve the resolution, which is patented. So a couple also of hardware solutions which are quite proprietary to our system.
And then the transparency window of the polymer, can you comment on that?
Transparency, what do you mean, wavelength range? Or
yes, exactly.
We go up to 2 micron. We even have done measurement up to 20 micron recently. So it works quite well. There are some areas where there are dips, but we can, if you need data, we can provide you on some reasons.
Okay. Thank you. And the shorter wavelengths?
We go down up to 450, 420, depends on the resin.
Very interesting.
Okay, thank you, Amir, and thank you, Joerg, for the presentation. I'm sure you'll get more requests, maybe in our after session that will start very soon.
Thanks for the invitation, Ivan. Thanks a lot.
You're welcome. You're welcome. Now I just pass the floor to Nicholas from MicroOptics.
I'm sorry, Ivan. There is one more question. I'm sorry for interrupting. It's from Alter Technology, William Dorwans.
Okay.
Hello,
William.
Hi there. Yeah, it's just a quick question. We're seeing more and more applications for cryogenic and for coupling as well too. Does the polymer, or would the polymer withstand cryogenic processing? Would it withstand low temperatures?
we have some 1 or 2 polymers which have been used in cryogenic applications.
Okay. Thank you.
Yeah.
Okay. Thank you very much. Nicolas from MicroOptics, please share what you have in mind.
Thanks, Ivan. Thanks for giving me that stage. It's been a very interesting meeting actually so far. I want to touch quickly upon one point which was mentioned a couple of times before, which really is that we should not forget in all these integration aspects and packaging approaches, we shouldn't forget electronics, right? Because in the end, you don't only need PICs, although PICs are great and can do a lot of things, but you typically also need some other electronic ICs. So what we've developing at MicroOptics is kind of similar to approaches that we've seen in the talks before. So we have an optical platform which routes light passively from A to B. But the key thing that stands out here is that we integrate this really with PCB technology, which means you can get access to state-of-the-art RF boards, for example, 100 gigahertz, which is interesting for telecom applications, for example. And you can add this with our passive waveguide technology, which then allows you to have boards similar to what is shown here. So this is one example of a glass substrate, glass interposer, which can be used to assemble your PICs, but also your electronic ICs, with the advantage that you not only have the optical connections, but also the electrical ones. This is another board. This is a really now an RF board. So you see, you can really get some also quite difficult RF capacities on such boards, and you can again integrate it with optics. So I think this is one aspect of all of these integration aspects, which adds to the difficulty of the entire systems, having the electronics on board as well. So this is an offer that we have. We have this technology which allows you to create these boards, to use those boards for packaging multi-chip or multi-port architectures. So we're definitely looking for partners, or also for some feedback, of what is necessary, what is missing, or of course to partners who have an advanced application in mind, which could benefit from this platform. So that's all I wanted to share. Thanks a lot for that opportunity.
Thank you, Nicolas. Thank you. This was very interesting. This polymer platform. Can you say if it's really scalable?
It is really scalable. That's actually the thoughts behind this. So in contrast to, let's say, a regular fiber assembly, where the packaging scales by the number of PICs, the idea here is that you have one substrate which is pre-patterned. So using photolithographic processes, so it means you can scale, you can add complexity without adding efforts, so to say. Yeah, so it's definitely meant to scale similar to PCB manufacturing technology.
All right. Thank you very much. I invite you to stay for a little bit longer to join our after session. And now I would just like to pass the word to our last speaker, Chris Maloney.
Ivan, I'm really sorry. There is one more question from Rolando for MicroOptics, and maybe he wants to have it.
Hi. It's not really a question. It's a comment. I wanted to jump on a comment that was done by the colleague at Fraunhofer, and it's also linked to the solutions made with polymeric materials. He was mentioning about using glass platform for packaging. This just to inform that at Ventoprint we actively work and provide solutions for fiber to chip, let's say, alignment and packaging solutions with our technology. So if you want to have any kind of solutions in that sense, please, you can contact us. It's what we can do for the community.
Thank you, Ronaldo. That's super nice. Ivan, I would like to have one more question that comes. Actually, it's a comment from Dimitri from Chilas. Dimitri.
Oh yes, it was about the cryogenic applications that William asked about, and I'm intrigued by these applications. In the field, I don't hear a lot of comments about cryogenic applications, but we had somebody nearby putting our lasers into cryostat at 4 Kelvin, and still squeeze some decent amount of photons out of there. So the first test with some hybrid integrated platforms, they seem to work. Yeah, so it's not a showstopper directly. I would expect the other way around, that it would not work, but yeah. That's it. Just a comment from my side.
Okay, thanks a lot. Thanks a lot, Dimitri, for the comment. And we are now ready to go to our last speaker, which is Chris Maloney from VPI Photonics. Chris, thanks a lot for your patience, and the rest of the people that have been here, but they're still here in the room. The floor is yours.
Yeah, thanks, Panos. Thanks, Ivan. It's been an interesting discussion today, and hopefully I can tie some of this together. I know you've heard from different foundries, you've heard from some different component suppliers. So at VPI Photonics, what our goal is to give you the tools to empower you to define the cutting edge. So hopefully you can go to some of these foundries or use some of these components in the future in your designs. And the way that we do that is through providing photonic design automation software. We've been doing this for over 20 years, and we like to describe it as being integrated, interoperable, and industry leading. So we integrate different design techniques at various levels of abstraction in a simple user interface for you. Our tools are also interoperable, so with many third-party vendors' software. So for example, it's interoperable with MATLAB or Python, but also some of the other EDA vendors like Keysight. And we get involved in a number of the European research projects. So we're a JEPICS partner. So we try to stay at the leading edge to provide our customers with these leading edge solutions. So to give you an idea of the levels of abstraction that we cover with our software, we actually cover a wide range, starting at the top at link engineering. So this would be more for like internet service providers to design their networks. And as we get closer to the PIC level, we can go down a level to transmission design. So designing your transceivers to see how they would operate in passing over however many kilometers of fiber. To model the nonlinearities in there, to see the end result, what the bit error rate might be for a transceiver, but also at the component design, and that's really where we're focusing today. We have tools for designing fiber optic devices, but more importantly today for photonic integrated circuits, and so this tool, the VPI Component Maker Photonic Circuits, interacts with a number of the different foundries that you heard from today, and we have access to their PDKs through that software tool. And then we also have device level software solutions for really getting into the deep physics of maybe a custom device that you're looking at. But what I wanted to focus on here today is really this photonic design workflow. And this is a little bit different. The solution is a little bit different for everybody. You might be jumping into the workflow at different points. But I want to show you just how this might work in practice, where we can start at the device level and actually look at different materials, and you can explore which material platform might suit your needs the best for the task you're trying to accomplish. And in the end, you can have some result where maybe you have an S parameter output from this level, and you can actually bring that into the photonic circuits tool. And you can bring those S parameters in, connect a number of your building blocks together to see how they might behave as a circuit together, and then take that circuit and use it at the system level. So you can use it as its own building block and move up a level to say, hey, my end application actually requires, X, Y, and Z. And so how does that component that you've designed actually affect the entire system? So we actually work, as I mentioned, closely with a number of the foundries. You heard from a few of them here today. I think in the room is LioniX, Smart Photonics, LIGENTEC, HHI, yeah, they're all here. And so we actually work closely with the foundries to get real measurement data, to pull in their information and use that as building blocks in our photonic circuits tool. So there's a few ways to get information into the photonic circuit design tool. One could be directly through simulation, so maybe from VPI Device Designer. One could be from actual measured data, more behavioral type models. And then we also have our own physical models. So there's 3 different ways to get your information into that circuit design tool, so then you can start to play around with that. And then once you have those compact model building blocks put together in a way that you'd like, you can actually export that simply into a number of different layout design tools shown here, and go to the foundry and have your circuit fabricated. And then finally, we heard from a few of the component suppliers today about some tunable lasers. You might want to explore how does that actually impact the entire system that you're designing for, what the application, the end use will be, and how that will affect the performance. We've also heard a number of times today about electrical and optical co-design, and putting as we get more integrated, the electronics and the optics get closer together, they might start to impact one another. And it's important to also take that into account and simulate those 2 different domains together and actually design around that. So we have a partnership with Keysight using their Keysight ADS tool, where we can actually go from the electrical domain to the optical domain and back to the electrical domain. And so it's just to give you one last slide here, just to give you more of a visual perspective of what this might look like. You can start at the photonic device design, where you can have a 2D or 3D layout view to define your device. We have different mode solvers here. We support beam propagation method. And you can use this or other means, like going to a foundry, to build your compact models to use as building blocks. So you can see here, this is a simple waveguide that we're highlighting here, but it might be used inside of a Mach-Zehnder modulator. And so you actually have the circuit level here, where we can take our output, we can pull those different building blocks together and design that modulator to work at a specific wavelength, to understand how does the voltage, you run voltage sweep to see how that impacts the performance. And then actually take that into the full system level and say, okay, well, I have some generic laser and laser driver models to drive that, to drive the laser, and see how, when I actually put this Mach-Zehnder modulator into the flow, how might it affect my bit error rate after passing through, let's say, an optical fiber. You can even have the receiving optics in this design as well. So just to answer the questions at the end, how might we help you? How could you help us? Well, we want to provide you the tools to take your ideas to reality. And we have a support team that can help you out along the way. And then we're also always looking for new partnerships and collaborators. Of course, we're already working with a number of the foundries, but we're interested to see how can we develop those PDKs further. If you're looking to use those foundries, if there's specific components that you'd like to see as building blocks, how can we add those to the existing PDKs? And then we're also looking to collaborate with you on different use cases. So I know how these hybrid PIC designs are becoming more popular. We're also looking for feedback and use cases on the electrical optical co-design as well. So thank you for your attention and sticking around this late into the meeting today.
Thank you very much, Chris. Thank you for concluding with your excellent talk. Does anyone have questions for VPI Photonics? I mean, with this design capabilities, VPI can be a very important partner for pretty much everyone. Rolando, did you have something in mind? Okay, Henning, please go ahead.
Maybe one question from my side. So if I'm right, you're on the PIC level with your design and co-design. My question is, do we have design approaches, co-design approaches for the next packaging level as well? So if photonic, or if a PIC is on an interposer and have to be assembled on a board maybe, then it needs co-design as well. Do you have software tools for that additional level, so more into the system or subsystem?
So it depends what you want to do. We do have tools that exist. I'll give one example. Maybe this is more around short reach inside the data center applications, where you might have some micro-optics that you need to interact with. So we do have some collaborations to do some co-design, specifically one with Zemax, where we can actually input or output the Zemax beam file to do some free space optics type of calculation. So we have a number of interoperability possibilities. So it really depends what you're doing, where the limitations might be. We may or may not have the solution you're looking for.
Maybe if we talk about co-packaging in the data center domain with switch PICs and transceiver PICs, and we want to put that on a platform with integrated waveguides, so it's not the fiber approach on the transceivers, more integration. So then we need electrical and optical co-design from one packaging level to the next, and that is an issue, an important and crucial issue, I think. And the question is, do you have tools to do optical waveguide design and appropriate bandwidth or signal calculations, and the electrical design, high frequency design on all these packaging levels?
So yeah, that's a good question. Maybe we can talk more afterwards. I don't really know exactly the exact task you're looking at, but in general, with the software is flexible enough to accommodate the various technology platforms that you're looking at. So it really depends the interactions at each level, what do you want to model in the end. We do have the partnership with Keysight, where we can take the electrical output and bring it into the optical domain and see how it will impact. But I think it depends on the technology platform, the materials that you want to look at. And with the software, it's pretty flexible, where you don't have the same limitations you would in the lab.
Okay.
You're free to explore that space.
Okay, thank you.
Yep.
All right, Tuan?
Yes, so a comment and maybe to help Chris a bit, that let's say what we see in this kind of design problems is you have the implementation part and you have the simulation or analysis part. And I think what Chris trying to say is that the VPI platform is very capable of simulating or analyzing all of that, but you also have, how do you actually physically lay out all your structures, not only in 2D, but in 3D. So it's the floor planning of the individual die. It's maybe where are the electrical bond pads, where are the high-speed RF bond pads, where are the optical IOs, and how do you that physically implement in a 3D fashion, and how do you then analyze the whole structure? And I don't know if Henning, if that's, let's say, related to your question.
Yes. I'm looking for design tools in the end to put both domains, optic of photonics and electronics together, and
and what you now see in the industry is let's say, both in the optical or photonics industry as well as in the electronics industry, is this trend towards co-packaged optics, where you now start talking about chiplets. And chiplets can be either stacked silicon die doing an electrical function, or can be stacked and die together doing optical and electrical functions. So there's a whole search of R&D activity, and actually some companies are already demonstrating 3D systems with interposers, with waveguides on the interposers, with RF tracks on the interposers. And EDA companies like Synopsys are starting to enable those kind of, let's say, also implementation problems. So floor planning, trade-off analysis, and then also the evaluation or the analysis is something that is it's happening today.
Yeah, we are working on that at Fraunhofer IZM in Berlin, glass interposer, silicon interposer, all these stuff. But for the complete system, or we can do all the technology things to build up such kind of system. But the system design and that is, and a good co-design on the system level, that is an open aspect today, I think.
Yeah, but if let's say if DesignCon is in a couple of days, so there you will see presentations in this direction. The EECS conferences, and I think end of May you will see forums about co-design and chiplets for electrical and optical functions. So it's I think driven from the silicon industry, there's already a lot of activity going on that maybe we can leverage or learn from for the benefit of the photonics ecosystem in Europe, or let's say the topics we're discussing today.
Well, because you mentioned the DesignCon, that I know, but the other one was.
I can send you a link, let's say, to that other conference.
Okay, good. Thank you.
I think it's EECS, but I'll double check.
Thank you very much.
And thanks for clarifying that, Tuan. I'll just add one thing. Yeah, we're more focused at the schematic simulation level, rather than the layout design.
Okay, thank you.
We rely on our partners for.
Thank you both.
Yeah, thanks.
All right, thank you very much for your questions. And let's thank our last speaker for today, Chris Maloney. Thank you very much for concluding this seminar. Let me kick in over here with this short presentation. So, right. So yeah, this was the agenda of today. We had a great number of speakers, and because this topic of hybrid photonic integration is obviously huge. Let me just try to summarize briefly what we discussed today. And we spoke about the photonic integration platforms based on silicon photonics, indium phosphide, and silicon nitride, and as well as other platforms as glass polymer and lithium niobate. We had presentations from the major foundries in all of those major platforms: Smart Photonics for indium phosphide, and LIGENTEC for silicon nitride, and an input from Soitec on the SOI technologies. So we've mentioned the JPICs, the Joint European Platform for Photonic Integration, that provides the MPW services for all our members. And so there seems to be a quite well-established value chain already that consists of companies that provide packaging and assembly technologies, such as Nanoscribe, that produces tools for hybrid assembly, phix, that provides hybrid photonics assembly itself, and companies like Chilas, that produce ultra-narrow linewidth lasers. Apart from this quite well-established technologies already, there is obviously still R&D in progress, and there are novel solutions popping up, such as those provided by SCINTIL Photonics, MicroOptics, and Fraunhofer HHI that work with polymer-based platforms. So overall, the conclusion of this meeting, I would say, is that the technology trend is now for growing maturity of the photonic integrated circuits. And as maturity grows, we should see the diversity of approaches to decrease while the complexity will increase. And with that being said, I would like to thank again our sponsors, ficontec, LioniX International, phix, OFS, SAS, MicroOptics, and Nanoscribe. And I would like to wrap up our meeting by saying that there is a huge future for photonic integrated circuits, and the EPIC, the European Photonic Industry Consortium, will bring you together in the future. So please stay tuned, and you're always welcome to contact me and my colleagues if you want a follow-up of this discussion. So with this being said, we're going offline now. We will not be anymore on YouTube. And everyone who is still in the room is